Great. So as Virginie said, I'm going to talk a little bit about joint modeling of longitudinal and survival data. So very briefly, a bit about who I am. So I guess I mainly work in methodology. I spend a lot of my time programming, as Virginie just said, developing new statistical models. I've worked in lots of different clinical applied areas at the minute, mainly in cardiovascular disease, cancer epidemiology. A couple of main areas of research, so I've thoroughly enjoyed this week. I think it's been my favorite conference for quite a few years. As you'll be glad to know, I work a lot in joint modeling of longitudinal survival data. More recently, been focusing on multi-state survival analysis. And of course, I spend a lot of my time sort of developing software, in particular in Stator, to go alongside the sort of methods, stats development as well. So some current projects, again, so I thoroughly enjoyed lectures earlier in the week, looking at multiple timescale multi-state models, and also some interval censoring incorporated into competing risks. As Virginie said, I'll say at the start, a little disclaimer, I do work in Stator. I'm also now employed as a consultant developer by Stator. But all of the work I'm going to talk about today, joint modeling, including the packages that I've developed in Stator, has been and continues to be done as part of my academic work. Now the lecture slides will be pretty biased towards Stator. I've certainly seen predominantly R all week, so I hope it's useful to get a bit of a different perspective. And there's lots of stuff in Stator, but I will go through and give a bit of an overview of lots of different packages certainly available in Stator and R. We mentioned the Merlin package, which I'll come to at the end if there's time. Okay. So a bit of motivation. I think we're all familiar with this sort of motivation these days. There's certainly a general trend towards being able to access a lot more data, so we can start to ask a lot more questions, and not just general questions, but more detailed questions as we get access to more detailed information. So of course, the need for appropriate statistical modeling techniques and implementations in particular is crucial. So there's a huge growth in access to electronic health records, certainly in the UK, where I used to work. Now in Sweden, we have it's a bit of an epidemiologist paradise. But we have access to biomarkers measured repeatedly on patients. So we have some nesting, we have hierarchical structures. Patients are then nested within sort of doctor, GP practice area, nested within geographical region, etc. So we have hierarchical structures, repeated measures, lots of different multivariate outcomes. Standard challenges, hopefully we're all pretty familiar with them, but they still tend to be quite often ignored. I flagged these two in particular. Be interesting to hear from the other speakers later about focus on fundamental assumptions, things like allowing for time-dependent effects in proportional hazards models, allowing for nonlinear covariates, how we link our continuous biomarker to survival, allowing that to take on nonlinear structures. And some of the neglected challenges, which I think we will hear some about later on this morning. Multivariate outcomes, so not just modeling a single biomarker, a single time to event, bringing these processes together, allowing for multiple biomarkers, competing risks, the extension, the list goes on and on. Within patient variability, I think Jessica's going to talk about that later on. Informative observation times. So certainly when we start to model electronic health records, patients go to the doctors when they're sick. So the fact that we have an observation can itself be informative. Generally within the joint model framework, we tend to ignore such, we make an assumption that the observation process is ignorable, essentially. So how valid is that? So of course, we need modeling frameworks that can accommodate lots and lots of different aspects as we start to ask these more detailed questions. Okay, so what is joint modeling? Joint modeling, lots of different names, joint simultaneous modeling. Essentially, we're looking at two broad interlinked processes. We have a biomarker process. I'm going to stick with continuous outcome today. And we tend to approach that with a linear mixed effects model. Alongside that, we have the time to clinical event, such as survival, time to heart attack, etc. And we're interested in bringing these two processes together. Now, we can tend to look at these two things in two different ways. We may be interested in the longitudinal outcome, estimating our biomarker profile over time. But then, of course, we may need to allow for informative dropout due to death. Flip it round, if interest is more on the survival context, which it tends to be with the joint model, and we're interested in estimating the relationship between underlying, in other words, adjusting for things like measurement error in our biomarker. So the underlying biomarker profile, trajectory, how it changes over time, and how those changes are related to our clinical event. So I think we'll probably see quite a few of these this morning. This is joint modeling in a single slide. I have patient level data, two patients, patient on the left, biomarker observations, starts off pretty low, steadily increasing values compared to the patient on the right, starts out at a similar value at baseline, but over time maintains consistently lower values. Given estimated longitudinal model applied to this data, conditional on this trajectory, well, my survival prediction for patient number 98 gives a pretty good survival prediction. So in this example, higher values of the biomarker lead to reduced mortality. Compare that to the patient on the right, maintains consistently lower values of my biomarker and hence much poorer survival prediction. Now, if we'd ignored all the repeated measures, we would have very similar values at baseline and almost certainly got much more similar predictions. So this is where we incorporate the dynamic nature of our biomarker process. We incorporate the repeated measures, how it's changing over time. And I'll talk a bit more about this. There are lots of different ways we can link elements of our longitudinal process. Excuse me. So at a point in time, we can link based on the estimated current value of my biomarker, how it's changing, the rate of change, whether it's going up or down, where we started. We can still link things like the baseline, et cetera, all to link these two processes to create what's known as a dynamic prediction framework. So joint modeling of longitudinal and survival. So as I mentioned, I'm going to stick with a continuous outcome to start off with today. So we model a continuous outcome such as things like blood pressure. So that's my YI. So for the eyes patient at time t, we have an observed value of my biomarker. And I'm going to assume a very standard linear mixed effects model. So I've got fixed effects, coefficients, I've got random effects, normally distributed random effects. So how we specify our trend over time, we could do this very simply, random intercept, random linear slope. We could incorporate fractional polynomials, splines in these design matrices. And I've got my residual level 1 variation, think of it as our measurement error in my biomarker, okay, all very standard. Alongside that, we have a time to event, such as time to death. And of course, we could approach this with a proportional hazards model. So the hazard rate for the ICE patient at time t, well, it's a function of my baseline hazard. We could model this parametrically, flexible parametric using splines, things like that. I tend to do a lot of that in my work. We could leave it unspecified, assume a Cox model. And we have the exponential of my linear predictor, so baseline covariance and my associated log hazard ratios. Okay. Now in joint modeling, we're interested in what can we do if these two processes, these longitudinal and survival outcomes, are related. Now this gives rise to such questions as, what is the trajectory of blood pressure, i.e. how it changes over time, impacts the risk of death? Alternatively, if patients with higher blood pressure are more likely to die, will this affect our estimates of the trajectory of blood pressure over time? So again, that's two different angles of viewing it, depending on which outcome is of more primary interest. So biomarkers are often collected repeatedly over time in parallel to the time to event of interest. So there's been a huge growth in joint modeling over the past 20, 25 years. Lots of different examples. They're growing every year as the benefits of this modeling framework, availability of software, usable software becomes just increases. So the classic well-known examples include modeling CD4 cell counts in patients with HIV and the time to progression to AIDS. Prostate-specific antigen, I know Cecile's done a lot of work in this area, modeling prostate-specific antigen and risk of prostate cancer recurrence. And serum bilirubin and primary biliary cirrhosis of the liver. It's one of the classic joint model example data sets, which I'm also going to use in this talk later. So the things that are important to note here is that we very much have subject level covariates with our biomarker, which are measured at multiple time points. So if we just use our baseline values of the biomarker, well, we're simply throwing away a lot of potentially both statistically and clinically useful information. And of course, interest may lie in whether a change in the biomarker is associated with poor or improved prognosis. In other words, could changes in our biomarker act as a surrogate for prognosis? Okay, so my example is extremely well known in the joint modeling literature. I think I've used it in at least 3 or 4 papers. 312 patients with primary biliary cirrhosis. Now, cirrhosis is a slowly progressing disease in which healthy liver tissue is replaced with scar tissue, eventually preventing the liver from functioning properly. So the biomarker I'm going to focus on today got just under 2,000 repeated measures of serum bilirubin. It's a measure of liver function. Patients were treated with either D-penicillamine or a placebo. And the outcome, time to event outcome of all-cause death, where 140 patients died. So our research question today is, how does serum bilirubin change over time, and are those changes associated with survival? Okay, so we can look at this from 2 perspectives. Excuse me. Longitudinal studies are often affected by informative dropout, i.e. due to death. Or again, flip it around, can we account for measurement error when looking at how a time-varying biomarker is associated with an event of interest? So let's take a look at the first approach. In a longitudinal study, often missing data can be intermittent, could be potentially ignorable, and of course it could be informative. In other words, it should not be ignored in our analyses. Now, if the value of a biomarker is related to your risk of death, say higher values increase your risk, then over time, patients will drop out due to death and you're left with a healthier population. In other words, we have an informative dropout mechanism that we need to account for. Now, I think it's easiest to visualize this aspect through a little simulated example. I'm a big fan of simulation. So here I've simulated longitudinal data for 100 patients. So each light gray line represents a patient's biomarker profile. It's measured annually. And my thick black line is simply a Loess smoother. So I've simulated longitudinal data with no dropout. Okay, over time, 0 trend. So I've simulated from a curve with 0 mean intercept and 0 mean trend. Okay, complete observed data, no problems. We can estimate our unbiased intercept and slope. Now I'm going to reset my seed, but incorporate a dropout mechanism relating to higher values of the biomarker, increasing your risk of dropping out of the study. Reset my seed, so I have exactly the same simulated observations, but now I've incorporated this dropout mechanism. And what we see over time, we start to lose observations with higher values of the biomarker. So we see the area of my plot here starts to be missing. And if we estimated our curve over time, we would estimate this downward trend, when in fact, none exists. This is still my truth. This is still my true trajectory function. But due to that dropout mechanism, higher values, meaning you've got a higher risk of dropping out of the study, we would obtain biased estimates if we ignore such a dropout mechanism. Okay, so now we're going back to the survival analysis focus, which I'll continue with for the rest of my talk. So how does a time-varying biomarker impact the risk of an event? Lots of different approaches we could take. Time-varying covariate. Problems with that approach, it assumes that the biomarker doesn't change between observations, so we're working with a pretty biologically implausible step function. We ignore measurement error as well. Two-stage model, computationally efficient, but uncertainty in the first stage is not carried through to the second stage. So this is where we fit a linear mixed effects model, obtain predictions, and include those predictions as a time-varying covariate, excuse me, in our survival model. Unsurprisingly, joint modeling solves these issues. We can account for measurement error, utilize all the available repeated measures, reduce bias, and maximize efficiency. So as I've mentioned, joint modeling arose primarily in the field of AIDS, relating CD4 trajectories to time to progression to AIDS in HIV-positive patients. Lots of development in cancer, particularly in prostate cancer modeling. Important thing is to think of as two sort of core components that share some parameters. Linear mixed effects model for my biomarker, time to event proportional hazards, let's say, model for my survival outcome, and we share some parameters. Okay, so continuous longitudinal outcome, and I've got my M, my trajectory function, which is my function of my fixed effects and my random effects, which is representing the true unobserved value of the biomarker, having taken out this residual measurement error. Define my survival submodel. So if I first define my capital M, which is essentially the collection of the history of that longitudinal biomarker, it's going to be the true unobserved longitudinal profile up to time t. Assuming a proportional hazards model, I link my hazard rate at time t and allow it to be directly dependent on the estimated value of my biomarker at the same time t, multiplied by my alpha, which becomes what's known as my association parameter, which represents log hazard ratio for a 1 unit increase in my biomarker at time t. Okay, so I'm removing the measurement error and linking instead the estimated unobserved underlying true value of my biomarker. So alpha times my trajectory function tends to be termed the current value parameterization. Now we include the expected value of the longitudinal response in the linear predictor of my survival model. Now this tends to be quite intuitively appealing, since we're relating my hazard function at time t, at time of death, at a particular future time point. We clearly won't observe the biomarker at that same point t, but we link the expected value, so the estimated value, which is estimated from utilizing all the repeated measures over time to project that unobserved true value. Okay, so swapping to some a bit of Stator code to illustrate how we can fit these things in Stator. This is my data set. This is the data for a single patient. I've got the log of serum bilirubin, so that's my biomarker. I've just taken the log, repeated measures. This patient was on treatment. I've got my start times. These are the times at which the biomarker was measured. I've set up my at-risk time window. So this is how we would set up our data for time-varying covariate and survival analysis. And the final row of my event indicator is a 1 because the patient died after 5.27 years. Now, those of you familiar with Stator know that to fit any sort of survival time outcome, we simply have to st set, and it declares our data to be survival. And then off it goes, and we can use any of our st commands. So I simply declare my data set to be a survival data with that. Okay, first step, exploratory trajectory plots. These are really useful curves. What I'm doing here is plotting all of the observed biomarkers across time, overlaying a lower smoother, but plotting them separately between those that censored and those that were dyed. This is just to give an idea of any sort of pattern in the biomarker leading up to the period prior to death to start to indicate whether there's an association between the two processes. What we see here, you can see many of the observations, a sharp increase leading up to death. Now this becomes even more obvious if we adjust our timescale. I'm showing the wrong slide. Okay, it would be much more impressive if I showed the right picture. When I add the adjust option, what it will show is time since, time prior to event. So it aligns all of these profiles up to their time of death, and we can see the trend over time leading up to death. So it becomes much more obvious, but you have to trust me on that. Okay, fitting a joint model in Stator. We can use the STJM command. Very simple to fit joint models. Now we specify my longitudinal variable. I tell it my patient ID variable. For simplicity, I'm just gonna fit a Weibull survival submodel. STJM will assume a random intercept. I'm going to also specify a random linear trend over time. And I'm going to adjust for treatment in my survival submodel as well. Off it goes, fits my joint model using numerical integration. We can talk lots more about that in the later discussion sections about how we estimate these joint models. Parameter of interest is my current value. So by default, it assumes the current value parameterization. So I get my log hazard ratio. This is my alpha from before, quite a large log hazard ratio. So this is estimated, this is positive. In other words, higher values of my biomarker lead to an increase in the mortality rate. Highly statistically significant, so strong evidence that indeed a joint model is needed in this context. You also get my estimated variance covariance matrix from my random effects. So I had a random intercept and a random slope as well. Comparing approaches. So now I'm comparing estimates between my alpha parameters with 3 different approaches, assuming time varying covariance, fitting a 2-stage model, and then fitting the full joint model. So the first 2, somewhat, we can call them naive approaches, let's say. Building up, what we tend to see is that we see similar estimates of my log hazard ratio between the 2-stage and the full joint model. So the 2-stage is accounting for measurement error, but the uncertainty in the first stage is not carried through to the second. So we tend to see a larger standard error under the joint model, which is appropriately accounting for the uncertainty coming from both longitudinal and survival submodels. Come back to that question. Okay, so this is what we're doing. Rather than assuming step functions for biomarkers over time, we're postulating continuous time longitudinal model, continuous time survival model. So in other words, we can get estimates at any particular time. So we're smoothing out these step functions that we would get for both my longitudinal outcome and my survival outcome as well. Now, I mentioned a few at the start. There's lots of other ways to link the longitudinal and survival processes. I've talked about current value. Now I'm going to mention current slope. So we may not just be interested in absolute values of biomarker. Higher values increase my risk of death in the example we've looked at so far. But what if how the biomarker is changing over time? Its rate of change, its gradient, simply the trajectory function differentiate with respect to time. Okay, so how the biomarker is changing over time. Clearly, in many contexts, that may play an important role in predicting mortality, for example, in this context. So we can include multiple associations. So I get my alpha 1 in this context, linking the current value, and alpha 2 linking the current gradient. So it's not just how high or how low, it's whether the biomarker is increasing or decreasing as well. So we can look at this, just a little hypothetical example. Patient 1, slightly higher values, got same gradient over time. Interested in my hazard rate at 5 years? Well, under the current value association, if higher values increase the rate, we get a higher hazard rate for this patient compared to this one. However, if they had different trends over time and we linked through the current value association, well, we would get the same hazard rate for these 2 patients. Now, how they got there very, very different. And certainly where they're going, very, very different. Okay, so this is the sort of context where not only current value can be important, how high or low the absolute value, but which one is increasing at a higher rate. So although we have the same value here, patient number 2 is increasing at a much higher rate, which of course could indicate deterioration in their condition. Fit that in STJM, we simply add the deriv association option. Exactly the same model as before, but now I'm getting both my current value association parameter, it's been slightly reduced, and now I get my alpha 2. So log hazard ratio for a 1 unit increase in the rate of change of the biomarker at time t. Okay, so clearly both the current value and the rate of change are important in this example. And back to our conditional survival prediction. So I've gone full circle, building up, excuse me. I try not to choke. Excuse me. So we've gone full circle, back to developing our conditional survival prediction. So given now my estimated joint model, assuming we've modeled our longitudinal trajectory, our survival baseline all appropriately, we can then produce these dynamic patient-tailored conditional survival predictions, which I think we're going to hear a lot more about later this morning. So I won't focus on these too much. Okay, so I think I have hopefully 5-10 minutes left to whiz through some extended joint modeling. So this is a bit more focused on my current work, or the work I've been doing for the past couple of years. But certainly, I hope these next couple of slides are useful for sort of broader reading. Joint models really have been extended in numerous different directions. We're going to hear a lot more about that later this morning. Some core references: competing risks, different types of outcomes, multiple continuous outcome, delayed entry, recurrent events and terminal events, prediction. This is just a minor, tiny list of a huge wealth of literature developing, extending joint models in lots of important directions. Similarly, software, just as important in my opinion. STJM, what I've talked about today, GSAMS is a general structural equation engine in Stator, can fit lots of shared parameter models. Virginie's frailty pack can fit a huge range of multi-level survival models as well as joint models. Joiner ML by Pete Phillipson, Graham Hickey as well. Of course, Dimitri's JM Bayes, and now JM Bayes 2, I think we're going to hear about next. And of course, there's many others. There's Cecile's latent class package as well. So there's a huge wealth of software implementations which allow us to fit these models and use them in applied research these days. What I wanted to do was try and bring together lots and lots of different extensions all under one sort of framework. I wanted to attempt to model multiple outcomes, each of different types, allow the measurement schedule to vary across outcomes, so allow biomarkers to be measured at different time points, allow any number of levels, any number of random effects at each level, lots of different flexibility in how we share and link random effects between outcomes, of course, a reliable estimation engine, and also easily extendable by the user. So allow you to use the estimation engine, the syntax, the flexibility, but provide your own sort of little function which defines a new model. I won't focus too much on these. General level likelihood for essentially a multivariate generalized linear mixed effects model. There's lots of integrations, lots of numerical integrations going on there to calculate the likelihood. This is really the focus of the framework. And think of it as a sort of generalized additive model. Where I've got a link function and I'm mapping the expected value to a particular linear predictor. Now my linear predictor is a bit more complex now. I've got elements and components. Each component is made up of elements. Elements can be simple things. It can be a covariate, a vector of ones for an intercept. It can be a fixed effect parameter to estimate. It could be a normally distributed random effect. It could be a function of time. It could be a function of the expected value of a different outcome. So this is where we get all the special cases of joint models. And what the components are interactions between any number of these elements. So we could link the current value, but we can multiply it by a function of time to allow for non-proportional hazards, for example. We could do interactions between current values to allow for nonlinear effects of the current value of a biomarker on survival. The list is pretty endless. So I'm going to show some examples. And of course, each outcome model, who says we can only have a single complex linear predictor? We could have multiple ones. It's predominantly implemented in Stator. There's lots of stuff on my website. So lots of different distributions available. So each outcome can be modeled, can be a Gaussian, Bernoulli, beta, etc., etc. Lots of different survival type outcomes, allowing for left truncation, interval sensory. Models can be turned into a relative survival model. That's where we have the expected mortality rate. We want to estimate excess mortality rates. Element types, each of those elements, I mentioned a few, can be used to be a simple variable, can be a random effect, spline function, expected value of a different outcome, the rate of change, the integral of the expected value. There's lots and lots of flexibility in here. Okay, so this is my same data set, the PBC data set, slightly different format now. So this is the data set for 2 different patients, repeated measures of my biomarker and each patient's survival outcome. So we've got a single observation now. For this case, think of it as modeling each outcome in wide format. Now I'm going to show you syntax for 12 different models. I'm not going to change the data set. This is my data set. I load it into memory and off I go and fit all of these different models. So the command is called Merlin, stands for Mixed Effects Regression for linear and nonlinear and even user-defined outcomes. So this fits a linear regression model. Outcome variable, fixed effects, adjust for time, and specify a Gaussian family. Okay, nice and simple, linear regression. Add an interaction using the hash terminology rather, interaction between time and treatment, allow for different trends in the biomarker over time for different treatment groups. Now I'm going to add a random intercept. Random effect has to start with a capital letter, give it a 1 so it uniquely identifies it. I define the cluster variable, ID defines the hierarchy in my dataset, my ID variable. And each term over here, by default, estimates a parameter at the end, a coefficient. I'm going to constrain that to be 1. My intercept, fixed effect intercept is already there. So this M1 defines a random, a random effect with a normal distribution with mean 0. So I want to constrain that to be 1 to partition between the fixed and the random effects. Random slope, form an interaction between time and a second random effect defined at the same level of the hierarchy. So we get 2 random effects at the ID level. Okay, so random intercept and random linear trend model. Add a second model. I could model 2 biomarkers jointly within the same model. I've also got prothrombin index in my dataset. Why not? Let's model it with gamma distribution over time. But now I'm going to model time with a restricted cubic spline. So we model it flexibly with 3 degrees of freedom. So we use an RCS element type. Next, random intercept for my prothrombin index ID. So this is all one model. It's all shared. So we now have 3 random effects, all at the ID level. Okay. Now I can allow for correlation between the random effects, specify an unstructured variance covariance matrix for the 3 random effects. In Merlin, you can actually define t-distributed random effects. So we could add that and use 5 degrees of freedom for those. So relax the assumption of normally distributed random effects. Now I'm bringing in survival. So I've got biomarker 1, biomarker 2. Now I'm modeling survival. I'm pretending that I have core-specific mortality. You'll see why later. Modeling my survival time with a Royston-Palmer model that models the log cumulative hazard with restricted cubic splines, adjusting for treatment. And I'm modeling death due to other causes. There's no linking between the biomarkers and survival yet. We can fix that. I'm going to link the rate of change, that's the derivative of the expected value of this biomarker model, link it to survival, and I'm going to link the expected value of prothrombin index in here. So I'm linking each biomarker in 2 different ways. Nice and simple. Doesn't matter, we can change how we model or each of the biomarker models, we don't have to change this syntax at all. What am I doing now? Time-dependent effects, non-proportional hazards in my survival outcome. Treatment interacts with a function of time. Now I've squashed up these two longitudinal models, and I'm modeling death due to other causes and death due to cancer, competing risks. All of this within a single framework. So we've got a joint model of two biomarkers and competing causes of death.
2 more minutes, please, Michael.
Thanks, Virginie. Last thing, predictions. So I fit an extremely complex model. I still want to obtain easily understood things, easily understood predictions measured. So from this model, I can predict cumulative incidence function. I can get a marginal prediction that will integrate out those random effects for each of different things. In other words, we can get really easily interpretable direct probabilities from such a model. So it's a real focus of the engine. Lots more tutorials on my website, looking at the more simple examples. These are all the ones within joint model framework. There's also lots more about recurrent events, joint frailty models, multi-state models as well. Lots of future stuff, which I don't have real time to mention. There is a bit of Bayesian stuff coming. We can do a wrapper command called Morgana. I've inadvertently or accidentally called Bayesian's evil, if you're familiar with the Merlin and Arthur legends. But in other words, in terms of extensions for Merlin coming, penalization, cross-validation, lots of these important things that have been focused on in the literature recently are on the way as well. And I will finish with saying that there's a couple of short courses, assuming the world doesn't explode again this year and we all get back to normal. There's some short courses coming up which may be of interest. Thank you.